What is going on, YouTube? I hope all is well. You'll probably notice something a little bit different here. I'm actually utilizing some technology and being interrupted by my cat because he's just rude like that. But we are gonna. I want to clarify a couple things real quick. I mentioned in the other video, part one of this series, that this creates a voltage divider network, which is true. I feel like I didn't explain this portion of it very well. I mentioned that the signals for the high frequencies are diverted over this resistor. What I didn't really clarify was that this creates, these two parts right here create a knee, right? Or a corner frequency. And anything above that corner frequency will sail over this resistor unimpeded, creating basically a high shelf filter. So it allows frequencies above the shelf to sail over unimpeded. Everything below it will get muted to some degree. I think in this instance, 470K, it's about half the voltage, which equates to about 3 dB. So this creates a 3 dB shelving filter, if you will. Same thing for this here. It's just a repeat of this, except for this one is variable. I mentioned that as you turn this up, this becomes less and less effective. And then as you turn it down, this becomes more effective. The reason why is as you turn this up, all you're doing is shorting these 2 points out, okay? Electricity takes the path of least resistance. So if you short these out, this can't do anything because there's nothing that it needs to be able to do. But as you turn this down, the volume down, this becomes more and more effective because it essentially becomes more and more of whatever that is. Okay? So, yes, it is a voltage divider network, but it is a frequency-dependent voltage divider network. I just wanted to clarify that because I think some people might get that a little confused with how I put it. So, anyway, let's move on. I'm not going to get super crazy here with explaining this. I think it kind of explains itself, and Mr. Rob Robinette can do a much better job in his website or web pages and whatnot, describing all of this and how it works than I can. Because all I'm really doing anyway is just regurgitating a lot of this for you. What I love about this particular schematic here is that it shows the signal flow. I kind of wish it had the resistor numbers and the capacitor numbers because it makes it easier if you know what those are in order to build or design a layout. But that's not extremely important yet anyway, because I'm hoping that if you look at this and kind of understand the flow, that once you look at the layout, it will kind of just make sense anyway. So as you can see, another thing that's great about this particular schematic that Mr. Robinette has provided is that it tells you what each of the parts are: grid stopper, grid leak, cathode, preamp volume, cold clipper, attenuator, yada yada yada, all that stuff. That is great because it helps you understand the nomenclature that's needed in order to kind of design your own thing or even just build one. So if we follow the signal in from the high channel, you can see that it goes up and around and goes through the jack of the low input jack, actually. And then on into the cold clipper, from there into the next gain stage, into the cathode follower, through the tone stack, and onto the phase inverter. Now, if we plug directly into the low channel, it will skip the first stage because as it lifts this up, it will lift this portion of the circuit out of it. So that's how this kind of works. It's a neat little way to create a 2-channel amp out of something that has a 1-channel topography to it. So when you go into the low input, it bypasses this whole V1B stage here, and then you go in through the little attenuation network that we have, just like this guy here. It's the exact same thing as this, just different values in some of these parts. And then it goes through volume, which takes you directly to the cold clipper stage. Now, this is actually a very clever way to get a clean channel that's actually clean, and sounds pretty good clean too, mind you, but yet can still allow you to get some mild crunch, even with just the volume from the guitar itself. And the reason that is because it's a cold clipper. It's a cold clipper because it's biased very cold. And I talked about it before with this guy here, that the following stage from this point was a 39K for the SLO 100. Same principle here. This is one just happens to be a 10K. I mentioned briefly about biasing tubes. You can go with the load lines and all that jazz. Rob Robinette's has some of that. There's other resources that go into much greater detail and all that. But what it is with a cold clipper is that they have offset the bias of that tube. It is biased very cold on one half of the signal, or one half of its operating point, if you will. So as the AC signal comes in from your guitar amp, or from your guitar, period, one half is going to go into clip. It's going to distort or clip in this stage, whereas the upper half of the signal will not go into clipping. And that's because the bias is offset in this cold clipper stage. What that does is it causes asymmetric distortion, which is soft and gentle, excuse me. But it's also pleasing to listen to. It's got that bluesy kind of grit to it. It's smoother, and it has a very pleasing sound that people like. It is also a very large part of what makes the JCM 800 preamps sound the way that they do. So that is one value right there that you can play with if you want to change how this cold clipper works. But it's a nice way to get from a fully clean signal to a crunchy or gritty signal, at least anyway, before going into the meat and potatoes of what actually makes this amplifier chunk away, if you will. So this stage here is biased pretty hot with an 820 ohm cathode resistor. Pretty standard value for the plate, but this stage right here is what's actually doing the bulk of the distortion. By the time you get to this stage right here, this particular tube half, the valve 2A in this instance, is really getting spanked pretty hard. And that loads into a DC coupled cathode follower. I am not a fan of cathode followers. I don't like the way they sound. I don't like what they do. That is a personal thing. To me, they have a sound. I don't like it, but they do some things that are pretty cool and are helpful and purposeful, if you will. In this case here, it will help mellow out some of the grind from this tube's distortion. So it'll help mellow that out a little bit. And then it will help drive through the tone stack and punch the phase inverter enough to get some phase inverter distortion as well as you start cranking these volumes all the way up, right? It's not that you couldn't do it with a plate-loaded version of this design. So imagine clipping the cathode follower out and just going straight to the plate here. But it will do so more effectively by keeping it like this. So a cathode-driven circuit has more current flow or more current ability. It's less loaded down by the preceding stage. In this instance here, it just allows it to push through this tone stack, which sucks a lot of energy out of the signal, and keep on going to drive the heck out of the phase inverter. So as you turn this master volume all the way up, this phase inverter is getting spanked pretty hard. That's all. That's really all it does. Now, a plate-driven version of this, it just has less energy, less power to drive through the tone stack. So the tone stack will pull more energy out, giving it less spank on the phase inverter. I think that the phase inverter is a big part of the sound of a JCM 800 and many amps in general. A lot of people don't realize how much distortion is actually caused or created in the phase inverter long before it even reaches the power tubes. So if you've got an amplifier that only maybe has two stages, like say a champ or some other type of thing, a lot of times they often go through some sort of a phase inverter. A champ does not, but they go through some sort of a phase inverter. If you turn the volume all the way up and you were to take the power tubes out of the equation for them to distort, you'd find that you'd still get a bit of distortion, and it's from the phase inverter. And it creates the whole of the sum of all parts in this amp and how that sound is created. If that even made any sense. Don't bother. Don't listen to me. Whatever. Anyway, let's look at a layout of this. So right here, we see that schematic in this as a layout. This is built on a turret board. One thing that I had mentioned, I wish, is that they had the numbers on here. You know, R1, R2, C1, C2, and stuff. They don't have the pin numbers on the tubes, so it's you kind of have to count with me here. But on valve 1A, V1A, the plate is number 1, the grid is number 2, the cathode is number 3, 4 and 5 are the heaters, and then you have 6 is the plate for this tube, V1B, or this half of the tube. So 6 is V1B plate, and then you've got 7, which is the grid of V1B, and then you've got 8, which is the cathode of V1B. Okay, I hope that makes sense there. So you've got 1, 2, 3, 4, 5, 6, 7, 8, and 9. 4, 5, and 9 are the heater circuit. So you don't really have to worry about those so much. Imagine just the yellow, green, and blue wires here kind of being the plate, the grid, and the cathode respectively. So if you see blue, you know that's a plate. If you see yellow, you know that's a cathode. And then where it's connected with green is a grid. So this is V1A side here, and this is V1B side here. So this is the A side, this is the B side. Okay, remember there's 2 triodes in a single 12AX7, and they're split down the middle if you can imagine. So when we come in through the high input here, you'll see it goes through the 1 meg grid leak, 68K grid stopper, down this wire here, and into V1B. And that correlates here, V1B. Alright, comes from here, goes out of the plate. Remember, the plate is where the signal flows out of in almost all instances here. This is the cathode. Cathode has the 2.7K with the 0.68, which they put the UF version there, but as you can see here, that's this here, right? Going back to here, we got the plate resistor, goes through the 0.022 coupling capacitor, which flows up and goes into the low input jack. When nothing is plugged into this jack, it shorts directly across to here, so it can flow back into the other side of the tube, which goes through the preamp volume, right? And so what you're looking at there is this network right here, okay? So it goes up through that input jack and then through that network. That's what all that is. So through the preamp volume, from the preamp volume all the way down into V1A, where it then repeats the process again. So V1A, that's the grid. And we go up through another coupling capacitor and then another grid leak and attenuator circuit, which is what this stuff is right here. So it comes in, comes out, and then it goes up and through, yada yada yada, through this little network here. How does it get there? Through this coupling capacitor, right? So here's the plate. There's the plate load resistor. 0.022 comes through here, and then it jumps over. It's underneath the board in this case, so you can't really see where it's going there. These little triangles, they go to ground, okay? So that's what grounding is. That's the 470 that goes to ground. And then from here it goes out, it comes on down, and goes into our next gain stage right here. Okay? From there, you can kind of see that it goes that 100K. That's how this works here. All right. Okay, so that's what that is doing. From plate, goes through here. That's your plate load there. Now remember, on the other one, it comes out from the cathode. So this is a cathode-driven stage here. This goes into the tone stack, right? That's why there's no plate-driven anything else here. So the plate is just taking the voltage from the 10K, and then the 100K is what feeds those two parts, okay? So this is the cathode right here, this cathode that drives the tone stack. This is the tone stack, or part of it anyway, which I don't know why they didn't show all the wires that come out, but in either case, all you need to know is that they go into these guys here, and then these all eventually feed over into the master volume, right? Master volume here. And then from the master volume, it goes out and into the input side of one half of the phase inverter. The phase inverter has two inputs. One of the inputs in this case is being used for the negative feedback loop, which creates the presence circuit. And then the other half is what is actually being driven from the preamp of the amplifier. So you'll see here that 0.022 goes into the grid of that tube. You have the 82K, the 100K. On the plates, you'll see the 0.022 coupling capacitors, and then the negative feedback loop circuit right down through here. So it comes in through the 0.1 UF. So you can kind of see all that there, 0.022, 0.1. And then each of those plates go out, and those are the coupling capacitors. A right here, these two different colors here, correlate here. Those go into the power tubes. These are the grid leak resistors. You cannot see that stuff in here. These are over here, those grid leak resistors. This doesn't go out that far, but that's what that is. And then you'll notice here that that's connected to this little network here. This is the negative bias supply that sets the bias for the power tubes. There's a negative voltage that is varied through this part right here, which is actually a potentiometer, although you can't see it from here, but this controls the range. Well, between the two of these you can get the range and the amount of negative feedback that is supplied into the grid leak resistors here that set the bias for the output tubes. So that's where we're going to stop in terms of where we're at right now. We'll get into the power supply section of things a little bit more in other subsequent videos, but for now what you really just need to work on is seeing the flow of the signal through this circuit and how it correlates with this layout here. In other videos, we're actually going to take some sort of generic circuit, if you will, maybe not exactly this one, but another one, and then we'll make a layout that's based on that. If you can draw out the signal flow in a schematic, then you can make your own layout very easily, actually. The hardest part, I guess, is not having like R1, R2, R3, R4, C1, C2, C3, C4, and all that stuff. And the only reason I say that is because it's easy to go, okay, I know where R1 is, and then you can put R1 on here, and it just helps because you can follow the things along. That's why those things are labeled the way they are, is so that you can tie them all together a little bit easier. That's really it. But if you can follow the signal flow on a schematic, you can follow the signal flow on a layout or turret board. In which case, that means you can reverse engineer either one and take this and turn it into this, or take this and turn it into this. So I hope this helps greatly. If you enjoy this, please subscribe and stick around for other videos. We got more coming. We're going to start delving into other aspects here pretty soon, things like power supply, how to actually create layouts, different programs that you can do that with. And thank you so much for listening to me ramble, and well, we'll talk to you soon. Take care. Bye.